Starting with the name of Allah Almighty, who's most kind and most merciful. I, Fayaz Aman, with my group mate Amir Makbul, have worked on our final year project, that is electric vehicle charging station, under supervision of Dr. Muhammad Asim Samejo and co-supervision of Iram Asra. Here is the outline of our project, our presentation. That is, first of all, I will talk about introduction, then motivation, then problem statement, literature review, aims and objectives, methodology and hardware development, results and discussion, conclusion, and the last future recommendation. So here is the introduction of our project. So electric vehicle charging stations are classified on the basis of their ratings, on the basis of their charging time. So there are basically three types of charging stations. If I talk about, first of all, you can see here that AC slow charging. AC slow charging are also known as level 1 chargers. They are basically onboard chargers, and they are integrated charger in the motor drive. Means just we have to plug in AC supply into the car, and the conversion of AC to DC and DC to DC is done within the car. These chargers are also known as slow charging or level 1 chargers. After this, second type of charger is off-board chargers. You can see here, this is off-board charger. In off-board charger, the conversion of AC to DC or DC to DC is done outside the car, and onboard outside the charge, and also onboard charger is integrated within the car to charge fastly. In the last three AC fast charging, in which we use onboard charger, which is integrated charger in the motor drive. You can see here, this is AC fast charging, that is also known as level 2 chargers, and DC fast charging, which are also known as level 3 chargers, and AC slow charging, which are also known as level 1 chargers. So we basically we are working on level 3 DC fast charger using SST technology. So SST technology is based on DC fast chargers, have good capacity to charge batteries of electric vehicles as quickly as possible. So solid state, what is SST technology? Basically, SST is solid state transformer based technology, which is used nowadays and which is emerging technology in terms of charging infrastructure of electric vehicles. Why we are using SST technology? Because the size of charging station will be reduced. That is why we are using a solid state transformer based technology. So which thing that motivated us to work on electric vehicle charging stations? So here this is a slide. This slide is related to the motivation. The first of all, the fast growing of electric vehicles. As we know that the electric vehicles are increasing day by day, and the world is going to use of renewable energy. So that fast growing of electric vehicles, that factor actually motivated us to work on electric vehicle chargers. Second one is electric vehicle chargers are being imported in Pakistan. Especially if I am talking about Pakistan, in Pakistan these chargers are not manufactured. So EV chargers are imported from other countries, and that they are very costly. Third one, we are using basically SST technology, solid state transformer based technology. That is new technology, and we want to learn about this technology. So this is also a major factor that motivated us to work on this project. Contribution towards green environment, as early I discussed about this. And currently EV chargers are hot research topic in industry and academia. Electric vehicles are growing, so that it is very research topic in the industry as well as in academia. So this is the problem statement. What were the problems? The first problem is fast charging is expensive in Pakistan. As I already discussed that Pakistan is importing the chargers, electric vehicle chargers, so they are very expensive. If we make it in Pakistan, then it will not costly. So fast charging is expensive in Pakistan, especially. Second problem is high charging time. The level 1 chargers and level 2 chargers take much time to charge a battery of electric vehicles. So to reduce the charging time, it is a big problem. So we have to solve this problem to charge as quickly as possible. The chargers which are available in the market that are low efficiency and having low efficiency, and the charger we are working, it will be the most efficient. Available sizes are too bulky in size. Level 1 chargers and level 2 chargers are too bulky in size. So we are using solid state transformer technology to reduce the size of chargers also. So here is the literature review, and literature review, we have reviewed the literature from different sites, different papers that are available at different areas. So infrastructure of existing chargers. Conventional AC onboard charger, level 1 and level 2, as earlier I discussed, level 1 chargers and level 2 chargers. Then conventional DC off-board chargers that are level 3 chargers. These chargers are available in the market. Now we are using nowadays the technology is moving to the SSD based fast charging infrastructure because their efficiency is 94%. Now, what are the aims and objectives? Design and implement an efficient battery charger for electric vehicles, to reduce size of charger by using SST technology, to reduce the charging time of batteries, hardware implementation of project. These are the aims and objectives of our final year project. So how we will implement, this is block diagram. We will implement this project in hardware form by using this block diagram. As you see that we will basically supply AC supply here, and then AC supply is rectified and changed into the DC supply. Then DC supply is supplied to the inverter, and that inverter basically changes DC supply to the AC supply with high frequency. We are using here inverter because of high power and high frequency, to get high power and high frequency. Then we will use high frequency transformer, that is basically step down transformer, that will step down the voltages and current increases. Then AC voltages are rectified into the DC output. This is basically block diagram which will be implemented to get hardware of the electric vehicle charging station. So first of all, we have worked on the inverter. So what are the requirements of inverter? The output of the inverter should be 5 kilowatt. That is basically need and requirement of the inverter. The input voltage should be 120 voltage DC, and output voltage is 100 voltage AC, and output current is 50 ampere, and output frequency should be 30 to 50 kilohertz. So this is the PCB designing of our inverter. The operating frequency of this inverter is 5 kilohertz. The capacitor value that we will choose, is 47 microfarad to get desired output waveform. Input voltage is 18 voltage, and this is the PCB designing of our inverter. And after all, we have got this milled board, and input supply voltage is 18 voltage DC, and it worked successfully. Now here you can see here the output of the inverter, which is almost AC sine wave. You can see here that the frequency is 4.99 kilohertz, almost 5 kilohertz, and V amplitude of this waveform is 16.68 voltages. It works successfully on 5 kilohertz frequency. Now we test our inverter on 30 kilohertz. You can see here 30 kilohertz. By applying 30 kilohertz frequency, we have to change also change capacitor value, that is 220 microfarad. Then we also added fuses. Why we added fuses? Because the leakage current flowing in high power MOSFETs into the HCPL 3120 IC. So this IC can be burned out. So for the protection, we have used fuses. And this is the inverter output, that 30 kilohertz on 30 kilohertz supply, 30 kilohertz frequency. You can see here that the output frequency of inverter is 28.52 kilohertz, and V amplitude is 15.97 voltages. You can see the output waveform of the inverter, which is almost AC sine wave. Now here is the power supply. So power supply basically we made for the purpose to supply the Arduino and Pulse generation IC that we are using in our project. DC 5 voltage is required to Arduino for operation, and DC 15 voltage is required to Pulse generation IC for operation. So we have decided that we will supply DC from 220 voltages AC. Here is the circuit diagram of our power supply. You can see here that we have used a step down transformer, which actually changes AC voltages from 220 to 12 volt. Then we have used rectifier IC that will change 12 voltage AC into the DC. Then we have used capacitors so that it can filter out the AC supply, AC components. Then we have used regulator IC, 5 voltage regulator IC, so that it can give us linear output of the 5 voltage DC. And this is 5 voltage DC, and for 15 voltages we have used 15 voltage regulator IC. And this is the PCB printed circuit board of our power supply. You can see here, this is the transformer, the rectifier IC, then capacitors, regulator IC, and this is the output of 5 voltage and 15 voltages DC. Then we have also used high frequency transformer. As I have already discussed, high frequency transformer used in SST technology. So the working principle of high frequency transformer is same as the conventional transformer. HFT operates using same basic principles as standard transformer. Primary difference is to operate at much high frequency, that is 20 kilohertz to 1 megahertz. What are the benefits of using high frequency transformer? These are the benefits of using high frequency transformer. Size is reduced, less copper wire is used as number of turns are less, then reduces copper losses, increases frequency. Then we have tested the high frequency transformer by applying 35 kilohertz frequency, and we peak to peak 19 voltages. You can see here the ratio of the voltages is matches 9.20 and 5.6. The voltage ratio of our high frequency transformer is 10:6, and you can see here the applied frequency is 34.97 kilohertz, almost 35 kilohertz. Then we have also used rectifiers, single phase rectifiers, to convert AC voltage into the DC. So we tested it individually. So you can see here we have applied 220 voltages, and then we have tested DC supply by connecting the DC bulb. You can see here it is working properly. Then in the final results, we have coupled all the components. You can see here we have coupled rectifier, then inverter, then transformer, then again rectifier, and we have connected the 15 voltage 15 watt load. You can see here input voltage is 24 voltage AC, and output voltage we get 12 volt DC and 1.26 ampere current. And this circuit, by coupling all the components, this circuit worked successfully. Then you can see here the demonstration of battery charging, as we claimed that we will charge the battery. You can see here that firstly we have discharged the battery 11.30. Then we have charged the battery on same by coupling all components of our project. You can see here 11.67 means the battery is charging, 12-volt battery is charging in progress. Now, feature recommendations. Design can be extended to 50 kilowatt, and medium voltage 3-phase from grid can be used for extra high power. Current capacity of design can be extended. Communication between charger and battery, and last product could be designed to sell in the market. So here is the demonstration. You can see, first of all, we have discharged the battery, and you can see here we are discharging the battery by connecting the 15 voltage load, 15 watt load. You can see here it is discharging, and it is up to 11.2 voltages. Now you can see here that it will charge. It will charge 11.90 by connecting it into the output of this this circuit. You can see here it is charging, and at most 11.90 we got fully charged, that is 12 volt. Thank you.